Why are waves important? So waves, there are various topics that have to be discussed under waves. So waves like mechanics and heat is a separate topic of physics. So there are various topics, as I mentioned, to be discussed under waves. So I'll be explaining to you in successive videos about the topics on waves. So in this video I'll begin the topic of waves and I'll explain it to you about the characteristics of different waves. What are the characteristics that are common and how we can find those characteristics and why those characteristics are important. So waves have various characteristics. So before going explain you what are the characteristics of waves, I'll explain you what a wave is. So a wave is actually an energy or a particle or an object. For most reasons, wave is actually an energy transmitter. A wave allows energy to be transferred from one point to another some distance away without any particles of the medium traveling between those 2 points. So wave transmits energy. Now you can see an example in this picture, in that now this is actually a sea wave, right? A sea wave, and this is colliding with a lighthouse or some building like that, and this might cause the destruction. Now, you know, in the case of tsunami, so even in the case of you can see in the case of earthquakes or in the case of floods, there may be many destructions to buildings and other properties, even to human lives. So these are some examples to clarify or to prove that wave transmits energy between 2 points. Now this energy is transmitted to these buildings, and as the result of that energy, the binding energy of these particles may break off, so the building will totally as a unit will collapse. So as a conclusion, a wave allows energy to be transferred from one point to another. So that's it about a wave. So now I'll explain you about the characteristics of a wave by considering a simple example. So for example, let's take a simple wave. Now you may have studied various types of waves from your junior days, and you may have seen what a wave is and how a wave is formed, how different waves are formed. Even if you are not familiar with the topic of waves, you may have practical experience that in day-to-day situations. So a practical wave looks simply like this. It has places called the crest and it has places called the troughs, and the maximum displacement from this is called the amplitude. I'll explain it to you in the next few minutes. So the points with the highest displacement are called the crests, and points with the lowest displacement are called the troughs. However, actually, if you disregard the distance, now this is called the mean or the base of this wave. So this is the zero amplitude or zero particle movement. So these 2 points, actually these 4 points, this point, this point, this point, and this point corresponds to those base points, what you call. There's no displacement from the mean position. So this is the mean position, and this is a graph for the distance over the displacement. So if you disregard the sign, the distance from the main base or this x-axis, like the horizontal axis, to the highest point, or which is the crest, is the same as that distance from the base to the trough, right? So crest and troughs are actually same distance, but when you take the displacement, we say that the highest displacement is the crest and the lowest displacement is the trough. Now as you identified about the characteristics of a wave, now another important thing to mention here is that there are actually this shape of the wave, right? The shape of the wave is actually a repetition. Now you can see that this part of the wave here is completely identical to this part of the wave, right? So that's about the repetition, and you can see the repetition of the wave pattern, right? Wave pattern throughout the distance, right? So if we extend in this direction or in this direction, you can see that this part will be repeating at regular intervals as this part, right? As is this part. So actually this is a repetition. So this is very somewhat similar to the concept that you learn under simple harmonic motion or circular motion, right? So having explained about the characteristics of a wave, now let's derive a simple relationship between these quantities. Now I explained to you about the amplitude, and so now what is the wavelength, right? So wavelength is a concept like this. Now if you have particles at the same phase, now what I mean by phase is that the particles are in actually behave in the same manner or in a similar manner. Now if you take a simple example for this particle, when you actually drag the wave in this direction, this particle moves upwards. So this part, although we see that these two actually are touching the distance line, so we also call the mean baseline or the mean line or mean displacement, this line distance axis. So although we see that these two particles are touching the base or the mean displacement, actually what actually happens is that these two particles are not in phase, because when you drag the wave in this direction or in this direction, it is completely opposite to the behavior of the particles near a point like this. So when you select this point and this point, you can see that when you drag the wave in this direction, this wave tends to move upwards, and similarly here also the wave tends to move upwards. So what actually happens is that now these two points are in phase. So the distance between those two particles, this particle and this particle, is called a wavelength. Now wavelength doesn't have to be between two crests or two troughs, right? Wavelength can be between any particles which are in phase. Now consider a similar an arbitrary particle like this, right, which doesn't have a special position. So if you take another particle somewhere here which is in phase, the distance between those two particles is also called the wavelength. Now having explained about the wavelength, let's derive a simple relationship between the wavelength and the frequency. Now you know what is meant by the frequency. So within a single vibration, right, now you know that this actually is corresponding to a single vibration, right, single vibration. So within one vibration, this wave moves a distance that is equal to the wavelength, which is lambda. So if f vibrations take place within 1 second, so the total distance moved by the waveform is f lambda, because within one vibration it moves a distance of lambda, which is equal to the wavelength. Within f vibrations it moves a distance of f lambda. Now you know actually that the distance moved during a unit time, or distance moved given a unit time, is actually the velocity of something, right? So you learn that in the other concepts of mechanics. So actually the velocity is the concept that we'll be discussing here. So the distance moved in unit time is actually the velocity. So f lambda is actually the velocity, right? So speed equals distance traveled in unit time. So we take the speed to be v, so v equals f lambda. Now this relationship is greatly important, right? Greatly important, and is true for any type of wave. Now we'll be using this equation in many concepts in the course of waves. Now not only in this video, in the videos that will be following also, in waves it will be vehemently used, and it's actually we call the basic, right, basic or the fundamental principle of the velocity, frequency and the wavelength relationship, right? So that's it about the characteristics of waves. Now I explained to you about the amplitude, wavelength, frequency, and the relationship between the speed, frequency and the wavelength. So having explained about the characteristics, now I'll explain about some types of waves. Now I don't actually have to explain you about the types of waves. You may have seen various types of waves in your day-to-day activity. For example, if you take a simple string and you tie it to some point and you sway it up and down, you can see a string. So that's a very simple string. And even in natural locations in which now say sea waves, right, sea waves, you can see a simple wave. Even if you throw stones to some pond or lake, you can see waves. So those are some simple occasions, right, where you can produce waves and where you can naturally see waves. So you can classify, right? There are various methods of classifying waves. So one method of classifying wave is based on the behavior of particles inside the wave. Now although there are various types of wave, I'll be discussing only I'll be focusing only on the concept of mechanical waves. So mechanical waves occur due to some mechanical system. For example, if you take a string, you tie it somewhere and you sway it up or down, it's actually mechanical system, right? So it obeys the concepts of mechanics as well. So those are the types of waves that I will be discussing. And another example, if you take a loudspeaker or some other audio transmitter, you can see that some waves are formed. So those are mechanical waves. So those will be the actually the basis or the base of discussion in this video and the videos that I will be talking in the next chapters. So depending on the characteristics of mechanical waves, mechanical waves can be divided into two types. So those are the transverse waves and longitudinal waves. So transverse waves and longitudinal waves are both mechanical waves, but they differ by a single quantity or single behavior pattern. Now let's identify what is a transverse wave. So a transverse wave is a wave which is propagated by vibrations perpendicular to the direction of travel of the wave. Now for example, as I explained a little while ago, if you take a string like this and if you tie it at some distance, at some wall or somewhere, you can sway this rope up or down. So actually you can see that the particles move up or down. But if you take the energy transmission inside this wave, you can see that the energy moves in this direction, and the movement of the particles is in the vertical direction and the movement of energy is in the horizontal direction. So what I mean is that these two energies, these two motions, or the energy and the movement, are perpendicular to each other. Now this doesn't have to be horizontal and vertical, this can be even inclined, right? However, although it is inclined or horizontal or vertical, the movement of the particles should be perpendicular to the direction of transmission of energy. So that is the main characteristics of transverse waves. So transverse waves can be seen at various occasions. For example, you can see this in the symbol of the string, as well as you can see C waves here. So these points we call about the amplitude. So this is the mean base, right? So and so forth. So the propagation of a transverse wave can be illustrated by this diagram. You can see that at these points you can see that this is above the mean displacement or the zero displacement point, and these parts are below the zero displacement point. Now these points tend to go upwards and these points now tend to go downwards, although they are considered positive. We consider them positive displacement. You can see that these parts go upward. Now from here to here onwards the particles move upwards, and from here to here and down up to here the particles move downwards, and again from here to here the particles move upwards, right? So they tend to move upwards and they tend to move downwards, so the energy is transmitted throughout the wave. So that's about the transverse waves. So let's consider about the longitudinal waves, and then I will explain about the difference between the transverse and the longitudinal waves. So the longitudinal wave is a wave in which vibrations occur in the same direction as the direction of travel of the wave. For example, if you take a slinky like this or a spiral here, you can say that if you compress, if you keep your hand here and if you compress this one and release, you can see some periodical movements. I explained to you about this concept in the concept of simple harmonic motion as well. So you can see periodical movements, and also you can see that some particles are much relaxed and some particles are much compressed, right? So these particles where the compressions occur, we call those compressions, and these particles where they are relaxed, we call them rarefactions. So what actually happens is that, now unlike in the case of transverse waves, though this is actually the main difference between the longitudinal and the transverse waves, unlike in the concept of transverse waves, now you know that the energy transmits already in this direction, now you know that already, but the movement of particles also is in this direction. Now they are parallel, right? They are parallel, so it's better to say parallel rather than in the same direction. They also move in this direction, right? Now in the case of transverse waves, although the energy was transmitted in either a horizontal or vertical direction, the particles moved in a completely perpendicular direction. Now another example of longitudinal waves is the occasion in which sound is propagated. Now you can see that at some points the sound is much relaxed, right? And you can hear that. However, in some points the intensity is very high, in which the particles move and particles are actually bounded together. Now these particles, the particles are very relaxed and these are compacted together, so there's a high intensity, right? So the sound is propagated like that way. However, although you see that there are compressions and rarefactions that occur inside these longitudinal waves. You can also denote a longitudinal wave in a similar pattern to that of the transverse wave. So here's an example. So if you have a rarefaction and compression pattern in longitudinal wave, you can make it analogous to the shape of a transverse wave, right? So the distance between two rarefactions is actually this distance, and you know that these particles, as I mentioned a little while ago, are in phase. So the distance between two rarefactions is equal to the wavelength, and similarly the distance between two compressions also is equal to the wavelength, and the distance between a rarefaction and a corresponding compression is equal to half of the wavelength, or lambda by 2. Alright, so that's it about the transverse and the longitudinal waves. So I explained about the difference as well. So my last topic in this video will be about the progressive waves. So what is a progressive wave? So progressive waves are actually, now as I mentioned in the first part of this video, we classify waves into different classifications, right? Different based on the different characteristics. So we actually classify these waves on the characteristics of behavior. Now another classification of waves is on the appearance or the transmission of energy. Now in this method, what you can say is that although the wave is, we don't have to care whether the wave is mechanical, that means transverse or longitudinal, or electromagnetic, or any other type of wave, but actually this classification greatly applies to the concept of mechanical waves. But as in the case of mechanical waves also, we don't have to consider whether it's transverse or longitudinal. We take only the appearance, right? What I mean by the appearance is that you will see in the next video, right? I will explain to you in the next video about this classification in detail. So in this classification we see about the movement of the particles, not whether the particles move in a direction perpendicular to the energy transmission or parallelly. So in this method we divide waves into two types, which are the progressive waves and the stationary or standing waves. So progressive waves and stationary waves are very much similar, but what actually differs a stationary wave from a progressive wave is that stationary waves are reflected back. Now you can see probably, now although when you sway a string or rope and you make a transverse wave by tying it to some surface, you can produce a transverse wave as you saw a little while ago. But what you can see here is that after some time, when the waveform reaches that barrier or the wall, it gets reflected back. Okay? It gets reflected back, and you can see some but actually what happens is that you can see some reflections as if the waveform is completely flipped over, right? Flipped vertically over. So that's it about the stationary waves. So in the case of progressive waves, what happens is progressive wave is never reflected back. So in a progressive wave, the waveform is never reflected back. And also in the case of progressive waves, you can apply V equals F lambda or any other characteristic equation at any moment. But in the case of standing waves, you can only apply the wave equations or waveform equations only to the progressive part, right? We don't consider the characteristics that we observed so far, so for the reflected part. So that will be discussed in detail from the next video onwards. So in this video I explained to you about waves, introduced about the topic of waves, what a wave is, how waves are formed, and how waves are important, and then about some classifications and about the characteristics of waves, and finally I am concluding with the topic of progressive waves. So I will explain the concept of progressive waves in the next video, stationary progressive waves and stationary waves, their differences, their characteristics, and so forth, as I explained for the transverse and the longitudinal waves. So thanks for watching this video, and see you then.